Oh yeah, we're back. So I've done some fiddling over the past couple days, and I've got the plot thickens, we'll say. So after I made the first video, I started thinking, well, it's not obvious why a cluster would be considerably more performant than a single node if there's the same total number of cores. Because no matter how fast your switch is, this is a 1 gig switch, but even if you had a 10 or 50 or 100 gig switch, there's still latency introduced by communication between the nodes. Excuse me. So if you have the same number of cores, then it's not obvious to me, or it wasn't obvious to me, how a cluster could possibly be faster. Until I ran the script again on a single node. And while I ran htop, which is just like Task Manager for Linux, but it looks nicer. And I'm fairly certain that it was throttled, because the script took, on one of these nodes, took, I believe, 20 seconds, 22 seconds. And in that time, in the beginning, all 4 cores were pegged out to 100%, and then 2 dropped down to like 5 or 10% for the remainder of the run until, it was complete. So I think there's some thermal throttling going on, which was interesting. Which I guess is not surprising. But anyhow, that's a detour. So I went back, and since it had been so long since I'd done it the first time, I reran the Python comparison on the cluster and the node, and it was similar orders of magnitude difference. And I kind of went ahead and jumped ahead because I was really curious to know, and I can't help but just like devote all my time and thought to one thing rather than trying to chunk it up over a couple of weeks. But I had ChatGPT write a Go script with the same algorithm. So it's checking n numbers. In this case, n was 10 million. And it's checking all numbers from 1 to the square root of n, so brute force effectively. And on the computer, it took 2.3 seconds. And on the cluster, it took maybe 10% less time. Maybe it was 2 seconds flat or something like that, 1.9 seconds. So not much difference, not much performance increase running it on the cluster over the laptop. And I found that really interesting. Because in my head, I'm thinking, well, maybe Python's MPI library is just that much more mature and robust. And or maybe Go's library is not as good, not as mature, not as well built out. And or maybe Go is already extremely optimized for parallel processing. And that wasn't very satisfying. Because I wanted to see like blisteringly fast cluster times. But yeah, implementing MPI in Go is not straightforward. There's, I think, 3 libraries. I found one of them was considerably better than the others, and it still had problems. But the one that I did end up using is in the script, is in the repo on GitHub, that I'll link down below. So the performance didn't get much better. So I went back and did some digging, and there were a bunch of print statements. With respect to the script that runs on the core, or the cluster, excuse me, there were a bunch of print statements. There was a whole lot of communication going on between the nodes. The worker nodes were sending back to the master node all of the primes they found, which I think for all numbers less than 10 million, it's like 60,000. It's either 60,000 or 600,000 primes. Probably 600,000 primes. I don't know. It's a lot. And they were sending them all back to the master node. So that was a problem. And then they were doing some other calculations, like how long processes took them being each individual nodes. And then, so I eliminated all of that. And then I realized, because I hadn't read enough into it, that I had been implementing a thing called Go routines, which is similar to Python's multiprocessing library, but Go routines spawn a process across cores. So there's a lot of different ways to slice the cake, right? You can in MPI, you can specify which node does which amount of work, which core does which amount of work, and potentially which thread does which amount of work. I was being diligent about assigning work to nodes and cores to make things nice and tidy and ensure that a core was only working on its own stuff at any given time. It had its own dedicated process. That process being, checking these numbers for primality from X to X plus 250,000 or whatever it was, 10 million divided by 16 cores. And Go routines were spawning each process, which caused that process to be spread out across cores. So then the data flow gets messy and cores are dealing with multiple problems at one time, and performance is lost. I guess suffice it to say, MPI is not a good time to use Go routines, or multi-threading specifically, because I think, I just started out with this. I don't know, maybe I'm just talking out of my butt here. It seems to me that each core should have its own set of jobs, and it should not be unexpectedly getting jobs at random times from other cores or other processes. But it's very, as a kind of a meta comment, I guess, it seems it gets into the weeds of computational theory and computation architecture really quickly, which is a little intimidating. It's been a long time since I took theory of computation in school, and I don't remember much of it. I guess at the end of the day, I eliminated all of the unnecessary communication between the nodes. I cut out where they were sending each other their primes. I don't care. I just had them send a 1 or a 0 effectively or a 1 when they were done finding all of their primes. And I had the master node wait for all 4 to report back and then stop the timer. So with that, I was able to go from 2 seconds to 800 milliseconds. So 800 thousandths of a second to find all primes, less than 10 million, which is much more in line of what I would have expected, and is blisteringly fast. I think the next thing is going to be, I think I'm going to stay with Go, just because I want to see blisteringly fast performance. Python is nice, but I want speed, baby. I want to try a compression algorithm and see how complicated that is to implement in MPI. And then maybe at some point I can give an overview of MPI video when I learn about it, because it's just a protocol, right? It doesn't matter what language you're using, but there is a good bit of nuance to it, especially when you're trying to go from fast to basically as fast as possible, which is what I want to do. If you ain't first, you're last. So yeah, 800 milliseconds. That's a big jump. So that is more in line with what I would expect, which is that a cluster is faster than an individual computer for any given language, and a compiled language is always going to be faster in general, which means a compiled language should be much, much, much faster on a cluster. So I hope you guys found this interesting. It's going to take me a couple days to work on the next one. In the meantime, this stuff is in the repo. Feel free to comment and tell me I'm stupid if I missed something glaring. Otherwise, thanks for watching. We'll see you next time.